Good afternoon. Thank you for joining us on our call today. My name is Katarina Ost from Transcat, and I'll be your moderator this afternoon. Our webinar topic is Managing Instrument Calibration and Maintenance. This topic is being co-presented by Jim Shields and Bob Crepps from Fluke. Jim Shields is the product manager for the process calibration group for Fluke. Jim has been active in the ISA and education and has actively supported and developed instrumentation curriculum. Jim has delivered instrumentation instructor training for the last 15 years to the USA Electrical Trades for the USA International Brotherhood of Electrical, worked at the National Training Institute annual training event. Jim has worked in the field of calibration and metrology, field and bench, for over 45 years. Bob Crepps is the Process Tools Technical Support Engineer for Fluke. He provides engineering level technical support and product training worldwide. Jim has over 30 years experience providing technical support and training for barcoding systems, fiber channel applications, and for the last 10 years, process calibration tools. We expect today's presentation to last roughly 45 minutes, and then we'll answer any questions that you have submitted. During any time of the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to Jim and Bob.
Here we go.
Hey,
Good afternoon, everybody. Good morning, good afternoon, everybody. Welcome and thank you for taking the time out of your busy days to join us today. I hope you find our presentation informative. I am Jim Shields, Fluke Product Manager, as introduced by Katarina, and Bob, whom you heard there. We just got unmuted and are fully empowered to communicate. So Bob, do you want to say good morning to everybody?
I do. Welcome everyone, and enjoy the presentation. We're gonna go through a couple slides and then I'll give you a demo.
Yeah, super, Bob. With that, let's kind of go forward and let's get with our topic. So our agenda today, we're going to talk, a little bit about what calibration is and why to calibrate. In the realm of calibration, we're going to discuss why is traceability and documentation important. The solution we're going to talk about today is a paperless solution that integrates documenting process calibrators. We'll abbreviate that as DPC for short, and calibration management software, and we'll abbreviate that as CMS. We're also going to discuss managing documented calibration records, how to interpret those records, and Bob is going to give us a live demonstration of the process that will be described in the PowerPoint slides. The calibration management software, the CMS, that he's going to be demonstrating is called DPC Track 2, and he will demonstrate downloading a software task to a documenting process calibrator, or DPC. That task is downloaded by tag number. That tag number that he's going to be downloading to the calibrator will be for calibration of a Rosemount 644 thermocouple temperature transmitter, and he's going to do he's going to pull up that task in the calibrator and do a calibration on that transmitter. Once the calibration is performed and stored in the memory of the calibrator, Bob will then upload the calibration result from the calibrator to the calibration software. and then review the uploaded calibration record. Once he's done with that, we'll be taking questions about the process, which we call a calibration work stream. And that's pretty much the overview of what we plan on talking about today. So elements of a process calibration system include the calibration equipment, as in the calibrator, accessories such as pumps and things of that nature. The instrument documentation is required. It requires management software to manage the data that these documenting calibrators capture. And your personnel need to be trained on how to utilize and operate these elements of this calibration process. The benefit to the user or the company that sponsors this in this process in their facility is consistent process performance and efficiency, product quality, reduced downtime, improved safety, and regulatory compliance. And another benefit is it maximizes the use of skilled personnel, maintenance personnel in plants who are becoming fewer and far between in the plants as the industry has experienced brain drain, if you will, the term that I've heard to refer to a lot of the skilled folks leaving the workplace. So why calibrate? Reasons to calibrate. Well, when I'm talking to customers that are engaged in this process, the primary reasons are the regulations that dictate practices within industry, the standards that are applied to various vertical organizations, and of course, some calibrations are a requirement for trade. Examples of an industry standard, for example, the Petroleum Institute is an industry standard. The Petroleum Institute, for example, maintains procedures and practices on a voluntary basis that puts companies in compliance with the more daunting regulatory agencies that are often auditing the industry. They're required for international trade. Sometimes the customer of the products that you manufacture in your facility require that calibration records be maintained and available for audit. And then, of course, weights and measures, which are often used in the batching of processes. A good example would be in the pharmaceutical industry, where any items that are being manufactured, the weights of ingredients that go into a process batch need to be carefully weighed, and of course measurements of that process batch, the temperatures and pressures that the batch is processed at, all have to be documented and recorded and measured by traceable measurement device instruments in the process. Another example, of course, is prevalent in a number of different industries, and that's custody transfer. I think the most common would be the transfer of gas or crude oil in pipelines from one entity to another. A good extreme example of that here in Washington State, where Fluke is located, we have a pipeline at the Canadian border where gas is transferred from a Canadian entity to a U.S. entity, and this is a fairly significant pipeline. And the transfer of this gas from one entity to another is a highly calibrated and accurate measurement process. So the error allowance in that particular process is very small, and records and calibration activities are required to ensure that the measurements on both sides of the equation, the entity delivering the gas and the entity receiving the gas, agree on the quantities, because a 1% error in this instance would be a significant amount of money and too much error for the financials. Another is the internal quality programs. The most common heard is the ISO 9000 program. I've heard it often stated that the technicians are going out to do their ISO calibrations, and those calibrations are documented as part of their quality program. And then, of course, last but not least, safety regulations, devices that are part of a safety and shutdown system that are critical to the safe operation of the plant and the safe shutdown of the plant, often require that those instruments have significant calibration records that can be reviewed by an OSHA auditor, for example. They're also important for the safety of the personnel in the plant and the public at large that lives in and around these plants that could potentially be affected by an unsafe incident or event that could occasionally happen at these plants. Ideally not, but sometimes that happens. So why calibrate? If the instruments are accurate when they come from the manufacturer, why don't they stay accurate for a year, for 2 years? Well, bottom line is all instruments and tools change over time, over temperature, over humidity, different environments, humidity, etc., temperature, and these all can be changing. Vibration can have an impact, and just simply normal use and wear and tear, and in some instances, abuse. And abuse isn't necessarily indicating that someone's not doing their work. It just so happens that in many instances, the processes are very difficult in the instruments that are making measurements of that process. And abuse is just a byproduct of the difficulty in the service in which the devices are installed. The bottom line, though, is no two instruments change the same in the same manner. And since that change is difficult to predict, these devices do require to be, at the very least, verified that they're accurate, that their performance is within specification, and adjustment in the event that it's not. So just a little talk about definitions. So what is calibration? This is a often misunderstood term. Often when I'm talking with the customers or trainees, when I talk about calibration, the first thing they want to do is get out an adjustment tool and go out adjusting things. But bottom line is adjustment is not necessarily calibration. Calibration is by definition the comparison of a measured value to a traceable measurement standard. So the measured value in a process example would be the milliamp signal, for example, that's being measured as the output of an instrument device. And the traceable measurement standard would be the calibrator with a certification that's making that milliamp measurement. And in the case of this intercomparison, this traceable calibration standard should be, as ballpark, 4 times more accurate than the device being tested. That's the most common rule of thumb in process that I've encountered. There are some other definitions of test uncertainty ratio, or TUR, that I've heard. The ISA has indicated that the test standard should be 10 times more accurate than the device being tested, but that's not always practical. An example of pressure, to achieve a 10-to-1 ratio, instead of being able to use a portable gauge or a calibrator, it's sort of a pressure gauge or a calibrator, you might have to take a bench calibrator out to do the calibration to get that 10-to-1 ratio. So the 10-to-1 is a great ideal, but it's not practical in most instances. And in the case of this intercomparison, in the event that the device that you're testing is found to be out of tolerance, adjusting to agree with the standard if necessary. It is possible to perform a calibration and intercomparison and find the device that's within tolerance and not have to make any adjustments at all and still perform a calibration. So a calibration can be performed with or without adjustment, but the adjustment is not necessary. It's only necessary if it's necessary to pull the device under test to agree with the standard within the allowable deviation. Accuracy, the definition of accuracy is the closeness of agreement between the observed value and the traceable accepted reference value. And then adjustment. Adjustments can be manual in the event of some of the old school analog instruments that had zero and span potentiometers that a technician would adjust their 4 and 20 milliamp signals with the application of a process signal on their inputs. But that technology is by and large being replaced by the digital technology, the smart instruments that have digital corrections of the signal. And the adjustment of that signal to match requires known input value to be applied. In other words, the input signal to the instrument before you make the adjustment needs to be a traceable source stimulus value in order to get the correct result. And again, adjustment is only necessary if the device is not performing as required. That brings up the topic of adjustment thresholds. Many technicians or organizations rather would have the technician make an adjustment on a device if it is greater than 50% of the allowable deviation or specification in error. Whereas if it's the error of the measured milliamp signal value, for example, is less than 50%, they would suggest that you don't make the adjustment. And again, that is there's not really a standard that defines when and where you adjust. That's typically a corporate standard or corporate practice, depending on the organization. So I brought up this term, traceability. Traceability speaks of an unbroken chain of calibration documentation. For example, our national standards organization here in the United States is the National Institute of Standards and Technology, or NIST. And that organization holds the, if you will, the legal volt, the legal ampere, the legal, all the various most accurate measurements and disciplines that are of significance to both commercial as well as science applications. So in this example, if you look at the very top of the standard, the national standards calibrates a bench calibration standard, for example, and that bench calibration standard has a document that covers its calibration. On that calibration documentation would be the serial number of the device, its calibration information before it was adjusted and after adjustment if it was required, the date and the time, who performed the work, and that document then documents the performance of the bench calibrator. Now that bench calibrator then can be used to calibrate different types of field devices. For example, a multimeter, or in this instance, a documenting calibrator. When that calibrator is documented by the bench calibrator, there's again another document that represents its calibration information. The serial number of the calibrator used to document that calibrator is recorded, who did the work. It's before adjustment information and after adjustment information is all recorded. And that becomes the traceability calibration information of that device. Now that field device would then be the device the technician would take out in the field to calibrate process instrumentation. That when the process instrumentation is calibrated, the performance of the device before it was adjusted is recorded. The performance of the device after it was adjusted, if necessary, is also recorded. The time, the date, and who did the work is also recorded and then documented on a record. So the point here is that there's an unbroken chain of documentation from the National Standards Organization right down to the documentation that covers the calibration of the field device that's out in the process making measurements. So why document and how? Calibrations may be required for regulations, required for quality standards, or required by your customers. They can assist in understanding the performance of a process over time, can be used to determine if a device is compatible with a particular process. If it's consistently out of tolerance, it may need to be replaced with an appropriate device. It also helps assess if a device needs repair or replacement. And in the event that a device is always within calibration and has very little deviation or error, calibration records might be able to help and be used in adjusting maintenance intervals, wherein the interval could be extended to reduce maintenance costs. Calibration records can take a number of different forms. They can be manually recorded on a paper form with a clipboard in the field. They can be recorded on a tablet or portable computer in the field, and they can be recorded using a calibrator with documenting capabilities. And all three of these forms of documentation are all actively used in the field today. So in starting up a process, initially, the process, you would want to identify the instruments that are critical. Firstly, of course, in the lineup of critical instruments, you might want to be including the safety instrumented system instruments that are responsible for making the measurements in the safe operation of the plant, startup and shutdown. The environmentally critical instruments that impact water or air flowing into the environment and are regulated by the EPA. Quality critical devices that affect product quality and the value of the product being manufactured in the facility, and revenue critical instruments, as I mentioned before, especially custody transfer and other trade related weights and measures. Next, once the devices are identified, the interval needs to be defined for the instruments for maintenance to ensure that the desired accuracy is maintained. Ideally, the instrument will perform in tolerance when tested at the end of the interval. And in the event that the device is not within tolerance, that can cause difficulties with some industries. Sometimes that could mean product being scrapped or paperwork to fill out. So ideally, the interval between maintenances and calibration checks is such that the device is in tolerance when tested at that interval. And if not, then maybe that interval would need to be adjusted or shortened. And of course, the specifications and test tolerances need to be carefully considered. The test tolerances in process should be specified by the process engineer that was involved in the initial design of the plant and documented in such a way that that information can be passed down to the technicians that are doing the maintenance and calibrations. If that test tolerance documenting the allowed deviations for the process is not specified by the process engineer, oftentimes the instrument manufacturer's specifications data sheet is assumed as a fallback. That is not the ideal process and sometimes can end up in over calibration of those process instruments. But in the event that the device is critical and it's part of the quality control process, you must have some specification and document that defines what the specification needs to be it by the process engineer or from the manufacturer's data sheet. And the instrument to be tested and the calibrator to be used needs to be considered. As I mentioned, the instrument that's being tested, the calibrator should be approximately 4 times more accurate than the device being tested. And then, of course, define the procedures for the identified critical tags that you've defined in your investigation into which tags to put into the database to be managed. So the one of the elements of this process that I mentioned is the Documenting Process Calibrator. There's a variety of different manufacturers of documenting process calibrators. Of course, I'm showing the Fluke one. This is the Fluke 754. It will source and measure virtually all critical process parameters for instrumentation. It automatically captures results, the date, the time, the user, and the tag information. And since it automatically documents and there's no writing on a clipboard, for example, it eliminates manual transcription errors. Even typing information into a laptop, there's an opportunity to mistype in information. But in the case of using a documenting calibrator, what is measured is what is documented and stored, and the ability, or rather the probability of transcription errors are eliminated. These documenting calibrators are often supported by multiple calibration management software platforms. Fluke has a calibration management software platform we will talk about called DPC Track 2. But there are a variety of other calibration platforms from a number of different suppliers that are compatible and will communicate with these documenting process calibrators. And a couple of examples are products from Prime Technologies and their ProCal, or Emerson Process Management and their AMS systems are just kind of a couple of examples, for example, of these types of platforms. And a documenting calibrator coupled with a calibration management software platform completes a paperless documenting field calibration system. So the ability to go paperless by implementing a documenting calibrator in this calibration software is a big benefit. And in the case of most of these documenting process calibrators, they would have the HART communication functionality on board for in the event that the device that's being calibrated requires adjustment using HART communication protocol. Calibration management software. There's as I mentioned, coupled with a calibrator, complete the documenting solution. There are a variety of different types of applications. CMS is what we call calibration management software, but there's also CMMS, which is computerized maintenance management software with which these devices can also communicate with. And they vary in complexity and price from the entry level, which we consider DPC Track 2 an entry-level product. Its list price is about $4,000. But when you get to the more sophisticated computerized maintenance management software platforms, these software packages can get up into $100,000 and more, depending on the size of the application and the organization. So again, there's a significant variety of different applications depending on how the organization wants or needs to work and what they wish to gain and achieve with their software. So in calibration management software, you can create custom procedures. So for each tag number that you've identified that's critical in the plant, each tag can have its own procedure by tag number. With this calibration management software, you can upload results from a documenting process calibrator and store them in the database for later use or retrieval to show an auditor or quality inspector or some other entity or person in an organization that is looking for proof of a calibration on a particular instrument or tag. You can print reports to support ISO 9000 documentation. You can go into the software, and if multiple calibrations have been performed on a particular tag over time, you can view and report their history, do trending. And one other feature that calibration management software can bring to the party here is that in the event that a calibrator is returned for, let's say you return a 754 to Transcat for calibration, and the as found calibration failed, the milliamp measurement for some reason was out of specification. It doesn't happen very often, but it could happen. In the event that it does, you might want to ask the question, well, which instruments did this calibrator touch while it was in the field and deployed by a calibration technician? Well, reverse traceability allows you to use the software to find which tags in the plant were touched by that calibrator in order, beginning with the most recent to the least recent. And you can then go through and recheck those instruments to ensure that they're within specification, and if not, remediate and adjust them to within specification. Of course, with a fresh calibrator that you know has a good calibration on it. So reverse traceability is the tool that allows you to go in and solve any problems that may have been caused by the errant performance of the out of tolerance calibrator. So in the calibration management software, you can go in and query and browse and look at the information about the various tags. You can use basically just a sorting tool or a search tool, not unlike you would use in any other search application or database. And in this instance, we found a tag TTJ1234. It's a Rosemount 3144. It's in service, and it's a thermocouple transmitter. It's calibrated 2 times a year, and its next calibration date, well, it looks like this is a dated slide. It says it's due in 2011, so it's overdue for calibration, if you will. And inside the information about this tag, we can see further information about its parameters. It's a thermocouple transmitter. Its input is measured in degrees C. Its output is a milliamp signal. It has a range of 0 to 100 degrees C. Output is 4 to 20. And the specification for the device, the error allowed is in percent of range, and it has a 1% tolerance. Based on that information, you can see down below the allowable deviations for the milliamp signal based on those temperatures applied. And these are the test tolerances and definition that will eventually be loaded into the documenting process calibrator to test the device in the field to determine if it's in specification. Here's additional information. This discusses the configuration of the calibrator. For example, the source of the calibrator is going to be a thermocouple. We're going to turn on 24-volt loop power to power the instrument. We're going to measure current and et cetera. So with all this information, we should be able to download then a tag to the transmitter, or to the documenting calibrator rather. Now here in the software, based on a variety of different factors, you can select based on date-based criteria or you can look for other various elements in the plant using a query. For example, I could look for all tags due before this before this date in one section of the plant that are pressure devices, identify those devices, and then put them in the load list to load the calibrator. Then I load those into the calibrator, and then we go to the field to perform the calibration. Once in the field, make the connection. In this instance, we'd be using external power supply rather than the internal 24 volts from the 754. And the thermocouple output of the transmitter is connected to the temperature input of the transmitter, and the milliamp signal is being measured, and the 4 to 20 milliamp signal is being analyzed and calculated for error. When tags are downloaded to the Documenting Process Calibrator, there's a task list, and the task list has a usage count. This task list can be used as a punch list for the technician to know which tags he has calibrated and which tags he has not, based on usage count. When the calibration is performed and completed, the usage count changes from 0 to 1. And in an instance like this can constitute a route for the technician to go out and perform the calibration. Once the task is pulled up on the calibrator, the documenting calibrator can provide lead-in prompts in advance of the actual calibration. For example, walking through a lockout tagout procedure, or information in the procedure to tell the technician where to find the device, how to make connections, or who to call at the control room to babysit this particular loop while the tag is taken offline. The design procedures that are downloaded from the software define what's measured, the allowable deviation in the milliamp signal and the test tolerance, and the temperature value that the calibrator is going to source, and then the test strategy, which is a number of calibration test points that are being evaluated. Once the review of the procedure is complete, you'll notice here in this intermediate mode, the calibrator is ready to go out and perform a calibration. Here's the temperature that the calibrator is applying, 0 degrees C for a type K thermocouple, and it's measuring 4 milliamps, and 4 milliamps 0.064 is greater than the allowable test tolerance, apparently, because this error is showing in reverse video. Here, the error percent shows the deviation of the measured milliamp signal when compared to nominal. And at this point, the test can be run automatically or manually, and each calibration point accepted by the calibration technician. Once the calibration is completed, the as found document is being prepared in the calibrator. You can see the temperatures that were measured, the milliamps that were, or rather the temperatures that were sourced, the milliamps that were measured, and the errors percent of span. The accurate knowledge of the source is required. The source value and measured values of the calibrator need to be traceable. And the pass-fail assessment indicates that this device failed and it needs adjustment. And if I take a look and I graph the measured values versus the test tolerance, you can see that a couple of these points were out of tolerance and that adjustment is required. When the calibration is found is complete, the tag entry screen is displayed where the tag number of the instrument and the serial number of the instrument are recorded, and the ID of the technician or whodunit is recorded along with this information, along with the date and the time and the serial number of the calibrator. All are stored in the electronic record for later upload to the calibration management software. In the event that adjustment fails, there's two methods of adjustment. One is analog, and that's the example I gave earlier where old style analog instruments that have a 0 and span adjustment, where the milliamp signal, the 4 milliamp signal is adjusted with the 0 pot. potentiometer, and the 20 milliamp signal is adjusted with the span potentiometer. And that test is performed making the adjustments and assuming it's within tolerance, and then a linearity check at 50% to ensure it's inspect as well. On the other hand, in the instance of smart instruments, the adjustment is performed using the heart communication protocol. In this case, the heart communication protocol in the 754. In this instance, you're given the option to perform an output trim, which adjusts the 40 to 20 milliamp output signal, or the sensor trim that trims the input A to D of the transmitter to adjust the heart lower range value and the heart upper range value that are programmed into the transmitter and ensure that the digital output value that's coming out of that input A to D is accurate and correct. So after the adjustment is performed, an as left needs to be taken. In the event that no adjustment was performed, the as found can be taken as the as left, and no as left test incrementally needs to be performed, because if the as found test determines that everything is in specification, you're essentially done with the task unless your organization indicates that you must perform a trim, even though the test was within tolerance. The as left test is successful if all of the errors in the result are shown in forward video and less than the test tolerance. The tag, the serial number, and the technician information are again documented and recorded. In the event that the as left test fails, additional adjustments can be performed. If multiple adjustments are performed and the device cannot be pulled back in tolerance, that may be an indication that the device needs to be replaced. And if we take a look at the graphing of the measurements versus the test tolerance, a passing as left would have those measurements well within the test tolerance, indicating that the test was successful. Once the calibration is completed, the results are uploaded back in the calibration management software, accepted and reviewed. And in this instance, we see an instance of a record where both the as found and the as left failed. So this is an indication of a device that was not able to be adjusted in and would perhaps need to be replaced. One of the big advantages, of course, is being able to access that data, being able to print it and provide that information to an auditor or quality inspector. That data over time enables analysis. And by virtue of comparing that information over time, intervals can be determined by analyzing the as found results before the adjustment is made. And if the results are small, or the errors are small rather on your as found, perhaps this device could be a candidate for having its interval extended. With that, I'm going to pass the baton to Bob, if you will, and Bob is going to perform a live demonstration of what we've just discussed. So here it is, Bob.
Okay, thanks, Jim. Let me get my screen up for you. Okay, so I've got the DPC Track 2 software up and running now, and we've talked about the instruments. Jim went over that. I'm just going to go ahead and go to my upload download screen, and you'll see I've got a whole bunch of devices here, and I want to find that TT100, but there's a lot of stuff here. So like we were talking about, you can search, in groups and select items to groups. So we're going to go to configuration, and I'm just going to pull up this furnace here, and I want to find this TT100 right there. So it makes it real easy to find a device that you want to calibrate and get it ready to go. Let's take a look and see. I've got my 754 connected to the PC. I'm going to get the calibration info. And there it is right there. So 754, and it shows up on COM11. So we're going to select that, and we're going to initiate download. And it's going to ask you, do you want to it's going to automatically delete any other records that are on the calibrator. So we're going to continue that. And while that's downloading, I'm going to switch screens and bring up the SAM54. And you notice going through, it's getting the download, it's getting stuff deleted, and then it's going to follow through and it's going to download. We're going to download from the software that task that we want to perform. And there it goes right there. So once that's downloaded, now we're going to go ahead and put the calibrator into hard mode. Now you'll see I'm connected up to the 644 transmitter, and I've got my plus and minus milliamp measure and 24 volt output and heart through this cable. And then I've got a thermocouple type K in this case connected to the calibrator. So this guy's going to be sourcing the type K millivolt values to the transmitter to test it. So I'll go ahead and press heart, enable loop power, and then we're going to pull it, check for that device, and there it is right there, TT100. So go ahead and enter that. Now this screen is going to come up, and it's going to show you basically the information on there right now. Notice there's no source at this time, and that's why we got an error message. So we're going to go ahead and start the calibration. So I'll press the heart button again, hit that we're going to source type K thermocouple. Okay, so now we're at the as found screen. Now here's the part where you want to now bring up the task that we have downloaded. So we're going to press more choices, go into tasks, and there's that task. We'll enter that. Now it's going to automatically bring up the task into the SAM54. So the technician now, he's got that TT100 he wants to calibrate, and he's now bringing up the task to run. So you'll see information about the calibration, and then a startup message that Jim was talking about. In this case, I just put verify boxes open, but again, you could put all kinds of things before the technician starts the test. Okay, now here's the screen for the calibration setup. Notice everything is automatically been put into the calibrator from that downloaded task. So we know we've got the 4020 output. We're going to set the tolerance at 0.5%, delay 10 seconds between test points, a 3-up test, and it's 0 to 300 degrees C in this case. Okay. Now we're at the calibration screen. So we're going to go ahead and auto test. In this case, because we're going to automatically send the type K millivolt signal. So hit auto test. And this point, it'll do a 3-up test. So it's going to start at 0 degrees C, get that reading, after a 10-second delay, and then go to 150 at the midpoint. That was the 50% mark. And then when it's got that captured, it's going to go to the 100%, which is 300 degrees C. And you notice on top, you'll see the error that it's reading, the error percentage. And so far, it's looking pretty good. So you'll notice in the test result, it's recorded what was sourced, what was measured, and the error percentage. And notice there's no inverse video, so it passed the test. It met that 0.5% accuracy that we were looking for. So press continue. You'll notice it's going to log the tag ID number, the TT100, serial number of this transmitter, and then who did the test, which was me. Okay, now at this point, if it was out of spec, we would go ahead and do the adjustment like Jim was talking about. I'm not going to do the adjustment because we're already good to go. But you'll notice you go in there and you can make adjustments to both the milliamp output trim and to the input center trim of that transmitter digitally. So, and if we had to make adjustments, we'd go ahead and do the as left and repeat that same test that we did in the as found, but we're good to go. So press continue. You get the message as you complete the calibration. And you're back to the main screen. Now we can go to more choices now and check out the memory and see, yeah, there's that calibration that we just did. Okay. So at this point, we're going to switch back over to the software. And this was that download which was completed. So now we've finished the calibration. We're going to switch to the upload screen. Okay, we've got the 754 still connected here, so we're going to initiate upload. And so now it's going to take that calibration result that was recorded in the 754, and it's going to upload it. Now it's captured it. And at this point, we have the choice of either authorizing the record or skipping it. We'll go and authorize it. Okay, and then we can either save or delete the results off the calibrator. We're just going to skip that. And that's the upload. So let's run over to our calibrations now. And you'll see we've got the TT100 up. Now, if we want to see all the calibrations done to this guy, we'll just go over here, search for TT100. And you'll see all the calibrations done. This is the latest one that we did, so we'll go ahead and bring that one up. And if we go to preview report, we're going to see the calibration report that we have uploaded. So I'm going to pull up the screen a bit because it's kind of hard to see, but there's what it looks like. So you'll see the information about the, what was the instrument, company name, more information about that device from the instrument. And then here's the special part. Here's the boxes. This is where the actual data was uploaded from the 754. So you'll see in the first box, it'll show the nominal values, what the output was supposed to be. Here's what the actual as found was. Notice we didn't have to repeat the as left, so it just copied the same thing over. And then here's your error percent that was documented, and it passed. The second box is also important, especially for audits, because this shows what test instrument was used during the calibration. Okay, so we used that 754 that we were just showing you, the serial number of it, and when the calibration was done and when it's due next. So calibration successful, and that is pretty much the test that we wanted to look at here. So I'll go ahead and switch it back over to Jim.
Thanks, Bob.
Coming over. There you go.
There we go. So with that, I would like to, that's the end of our presentation, and I think Katarina's been collecting questions. I would also, while I have a chance, I would like to thank our host Transcat for hosting this session today. If you're interested in learning more, please feel to reach out to Transcat about the products we've discussed, or Bob and I, of course. Our emails are up here on the slide. And I'd like to thank you for taking the time to attend. I hope you found the information useful. And with that, I'd like to turn this presentation over to Katarina for questions and closing.
Thanks, Jim and Bob. That concludes our presentation portion of the webinar. We will now move into the question and answer session. Just as a reminder, if you would like to ask a question right now, please send it through the question box in your webinar controls. After the webinar, if you think of any more questions, like Jim said, please feel free to contact me with the email address shown on the screen. Okay, so we'll move on to our first question. What is the best way to inform a tech as to what standard to use based on the accuracy required? SOPs are sometimes too general.
The most, from my experience, the most accepted standard is the oldest one. And that's the MIL standard 45662A that basically defines that the accuracy should be 4 times more accurate. The standard should be 4 times more accurate than the device being tested. So, and again, that's a very, very old regulation that's being universally accepted in the industry. There are other types of standards that are much more detailed. For example, the 17025, for example, is an example of a much more arduous requirement for standards. However, for most instrumentation applications, that standard is beyond the purview of what the folks are being asked to do in the field. I see 17025 primarily being used in the industries that require a higher degree of rigor, for example, pharmaceutical. And another example of an organization requiring that degree of rigor is the Ford Motor Company, who has adopted 17025 as a regulatory standard. I think that the short answer, to a great extent, there's a variety of different organizations that have oversight, and depending on the industry that you're in, there should be an industry or an industry organization that for which there is voluntary compliance to, that has detailed in some way, shape, or form the expected device performance and how you would expect it to perform and document the information. So I would say if there's no cognizant overview or organization, the 4-to-1 accuracy of the test standard to the device is the standard. But otherwise, you would defer to then the organization that has purview on your particular industry.
Okay. Is the 717 Fluke compatible with the software?
I'm sorry, the 717 is not compatible with our documenting software. The 717 does not have the documenting capability or the ability to upload or download, but thank you for that question.
Okay. How many calibrations can be documented before uploading back to the calibration software?
I'll let you take this one, Bob.
Sure. It's pretty, we try to be conservative about it, but you can actually do at least 50 calibrations on the calibrator. Generally in a given day, like a super tech like Jim, he could probably do 10. But generally, 5 or 7 per day. Generally it's best to just do a day's worth and then upload the results, just so you don't have any issues down the road. But like I said, I've had customers with like 150 on there, which I said, what are you doing, man? Just upload every day. But yeah, it's so I would say 50 is probably a good number, that's the ballpark.
We have time for a couple more, so please submit if you have anything that you are thinking of. The next question is, what are the implied cost savings of adopting this process?
Okay, so cost savings is always a challenge to calculate. But if you think about the work method of a technician getting a work order to go out and do one calibration, the technician goes out, performs that calibration, returns to the shop, and then gets another work order. Whereas if the technician is giving a documenting calibrator with 4 tags loaded into the calibrator, there's a potential of certainly the technician doing 2 calibrations before the next break or lunchtime comes up, and potentially doubling the efficiency in the field. So in the case of comparing routes to work order based work, literally you can cut your maintenance costs in half by using routes.
Okay, great. Last question. What is the best way to get started implementing the paperless process discussed?
Well, I kind of in the slides I mentioned. First of all, identify your critical tags, and then once you've identified your critical tags, you're going to have to make a decision on your software. Does it need to be a single user standalone, or is it at an enterprise level that you want multi-users accessing the software simultaneously? That's going to depend a little bit on the size of your organization. And of course, the software that you select has to be compatible with the hardware, the calibrators that you have decided that you want to use in your facility. So I would say identify the tags, make your software and hardware selection, and then work on the implementation and getting the tags and instruments documented in the calibration software, so you can get started on doing calibrations. I would assert that the most critical devices are probably the ones that you want to start with. So rather than trying to start out with all 10,000 tags in the plant, start out with the first critical 100 and work your way up.
Okay, we actually got two more. Which unit will work with the software and perform the pressure calibrations to 5K PSI?
The documenting calibrator, the 754 that we were discussing, does have optional pressure modules that are accessories to the device. And those pressure modules vary in range from, for example, 1 inch of water, full scale, all the way up to 10,000 PSI. So the 754 calibrator that was shown, plus a 5,000 PSI pressure module and a hydraulic pump would be the tools I would suggest for use with the DPC Track 2 software to do calibrations of pressure instruments at a 5,000 PSI range.
Okay. What advice do you have for shops that are just starting to do calibrations and are using spreadsheets to record information?
We have sample versions of this software that are free to use. And the nice thing about having spreadsheets, if you've got a spreadsheet by tag that has all the instruments in your plant, often those spreadsheets can be used to populate calibration management software. So if you have the inventory of critical tags in a spreadsheet in some way, shape, or form, there's a good chance you could use those for to import into software to populate and create the tags in the software without having to type all the information in. But to get started, you can download DPC Track 2 free from Fluke. It's fully functional for 60 days. And getting comfortable with that product and deciding if it's meets your expectations or whether you want more might be a good first step to take.
Okay, I think that concludes our time for today. To find out more about Transcat's products and service offerings, please contact us at 800-828-1470 or on the web at transcat.com. Thank you for joining us today. We hope you got something out of today's presentation and that you continue to join us for future Transcat e-learning webinars.
Thank you, everybody. Appreciate your time.
Bye, everyone.
Bye-bye.
Bye-bye.